There is a framework in Tom Sargent's famous textbook entitled Dynamic Macroeconomic Theory in section 1.5 entitled the optimal linear regulator, which is very useful as a general framework for a class of dynamic optimization problems in which we have a quadratic one-period return function and a linear function that describes the dynamics of the endogenous state. Here we are going to study the deterministic version of the framework. There is an equivalent stochastic version which we may visit later. We will see. Okay, so we have an objective function. We are supposed to maximize this flow. Please note that there is no discount factor in the setting. These are quadratic forms, so this is the reason why we say that we have a quadratic one-period return function. Supposing that this linear equation describes how the endogenous state behaves under the influence of the control variable. So most importantly, vector xt is it is a vector. This is the state vector. Ut is the control vector. Matrix R is a symmetric negative semi-definite matrix. Q is a negative definite matrix. Both are symmetric. It is important that Q is negative definite, because if you for a negative definite matrix, multiplying this matrix from the left and from the right with any non-negative vector, we will have negative values. So actually this is a profit function. This is a profit function. Okay, so a positive definite matrix gives with any non-zero vector a positive number. For any semi-definite matrix, equality is also possible. It is important in terms of maximums or minimums, with respect to maximums or minimums, because for a positive semi-definite matrix, we have a minimum for the zero matrix. Okay, A is an NN matrix and B is an NK matrix. R and Q are appropriate matrices, so we can know their dimensions. So R, okay, we can be more specific. So R, given the dimensions of the state vector, it must be an NN matrix, and Q must be a KK matrix. Okay, and we assume that the return function, the t in the index refers to the transpose of the state vector, so it looks like this. So the value function is supposed to be quadratic too, where p, of course, given the dimensions of the state vector, is an NN matrix, and as such it is a negative definite. All right, on this ground, the Bellman-equation, of course the Bellman-equation is the basis. The Bellman-equation is the following. We are supposed to maximize with respect to u the following expression. We are just using the linear equation describing the dynamics of the endogenous state. So this is actually the state next period. All right. So at this point we need the first order conditions as usual. So we are supposed to derivate the Bellman equation with respect to u, the control variable, but we cannot do this until expanding the Bellman equation. So I am writing the same equation, but now in an expanded form, because this part is problematic because of the brackets. So it's gonna be easier for us to state the first order conditions on the basis of an expanded Bellman equation. Okay, so this is easy because everything we do, what we do is just looking into the brackets. It's not the final form because we can use the fact. Let me show you on this example. So we will use the fact that it can be rewritten in this form. This is one thing. And the other thing is in this equation, in this expression, some parts have nothing to do with u, the control variable. So let's collect only those parts in which we have the control variable. Okay, so we simply skip those parts where there is no control variable. The mass part of the optimal linear regulator is not too difficult but we must be precise. Okay. So now we can start derivating this function, okay, with respect to u. First, let's have the result in a row form. So this is only a preliminary result which we will check because we are working with a matrix equation and the dimensions are important. So after derivation, the equation which we have must be appropriate. So the dimensions of these four parts must be the same. So let's see the dimensions. Okay, this is a k1 vector. This is a vector actually. If we go part by part, we can see the dimensions within the multiplication. The first x is 1n, nn, nn, nk. So this is in this form. This is a 1k matrix, which I will write in red, because trust me, this is going to be the exception. The second, this is kn, nn, nn, and n1. So altogether, this is a k1 vector. And the last item is kn, nn. So we need to pay close attention to the dimensions of the vectors and the matrices, because the solution may make no sense. So everything is k1 with one exception. So properly written, we have the following. We need to transpose the second part. We are just transposing the second part. Okay? This is fine. And this is also fine. So I think it's the final form. Yes. I think it's alright. BTPBU. Okay, so this is what we have finally, which can be simplified. So finally, we will have this equation as the first order condition, which is supposed to be 0. Okay. And we find u here and here, and x here. So the whole guy can be wrapped up in this much simpler form. And we can realize that here u, the control variable, is the function. This is equation 1.43 in the Sargent book. So this is a function, this is an equation between u and x. So it can be translated into a function where the control is the function of the state. So actually, this is a policy function, a linear policy function. So this is the famous linear regulator of which we are talking in this seminar session. This is equation 1.44. This is a linear function, linear policy function that describes the optimum decision as a function of the state, and it can be wrapped up this way, where f is this very long parameter matrix. Okay. This is what we are looking for. But there is a fly in the ointment, because, okay, we want to describe the optimum choice as the function of the state. We have a function, but this matrix, which belongs to the value function, is unknown. So, yes, we know that there is a linear function, linear policy function, but we have no solution to this function unless we solve the Bellman-equation to find matrix P. So to find this matrix P, we are supposed to input our optimum policy function back to the Bellman-equation. It is true that the optimum policy, it is true that the optimum policy solves the Bellman-equation. So what we are doing is to rewrite the Bellman-equation on the basis of the optimum policy. It's gonna be rather long, so we must be patient and careful, because we can do mistakes. We can make mistakes. So we should try to be as accurate as possible. Okay. Second line. It looks very complicated, but in the end we will find the patterns in this equation, and then we will realize that it can be simplified significantly. So we need to expand the whole equation to see, to realize, to find what we are looking for. Okay, and from this we can realize that x and the transpose of x is it shows up, they show up in each part of this sum. So we can simplify this equation to this form. It's the same after omitting x and its transpose in each part of the expression. Okay. Next line. I think you have already realized that there is a pattern in this equation. So some parts of the expression, they show up time and again. So some parts cancel each other. Some parts can be squeezed into a single expression. And the last line it's very long, as I promised. Okay, so here we can realize that yep, some parts so what we should realize is the similarity between this part of the equation and this part of the equation. And between this part of the equation and this part. The latter two are the same. And what you should realize is these two parts can be squeezed into one by adding up. So this is what we are going to have. this very long part is very simple eventually, because these parts fall out. We can just cancel them, and we can simplify further the expression by realizing that this part and this part are the same. They are the same. So finally, this is what we have. Okay, I think I am over the top because I inserted an extra step to give you a complete treatment, but I think it was all unnecessary. Yeah, and so we have equation 1.46 which is important because this is an equation called the Riccati equation. This is a Riccati equation in which the matrix from the value function is the unknown. So we numerically, by iterating with this equation, this is what we are going to do in MATLAB in the next seminar session. This is very exciting, to find the numerical solution to this problem, to the Riccati equation. So we can solve it numerically by successive steps in MATLAB. This is equation 1.47. We have an initial guess, a zero matrix, and under certain conditions which are specified in the textbook, the other parts of the job can be completed by MATLAB. Okay. The next section, in the next formulation of the problem, we have a very similar objective function in which we need to maximize the discounted sum of the profit flow. If it is a firm, it is a profit function, as I have just mentioned to you. So there is a discount factor, in the case of which the original model is still useful. The only thing we need to do is to insert the discount factor appropriately. So let's try to do so. The Bellman equation is the following. It's slightly different. Yep. So we have the discount factor. Okay. And we maximize this value function with respect to u, the control variable, when expanding on this Bellman-equation, we have the following. So we follow the steps of the previous part of the problem. The only reason I am showing you this expansion is to urge you to be precise, because the discount factor must be in the equation. So we should put it before any part that comes from the second half of the Bellman equation. Okay, so by following the same steps as we followed previously, we can highlight only the relevant parts. We are on the way to the first order condition, and you can realize, you can see that some parts of this Bellman equation, some parts of it simply don't contain the control variable, so we have nothing to do with them. And now we are ready to write the first order condition. The first order condition. QU beta BT P A X and the sum is supposed to be 0. From this, okay, and the optimum policy function looks very similar to the optimum policy function of the undiscounted version of the same problem. It doesn't matter where you write, where you put the discount factor. So this is the optimum policy function. I'm just double checking. Okay, it's correct. This is the optimum policy function, and the problem, we have the same fly in the ointment. We don't know anything about P, the matrix of the value function. So this is an equivalent policy function which ensures which gives the optimum of the Bellman equation. So by putting this optimum policy back into the Bellman equation, we get the same, not the same, but very similar Riccati equation. So given that we have no quick solution, there is a job to do. So let's see what we have. I think it's simpler to restart this formal work, because by doing the math in the clear form, we'll end up in proper solutions. One can try to go back to the previous problem and try to find the places where the discount factor must show up. But I think he or she is likely to make some errors. So I think it pays to... Oh, geez. Not to try to save time. This is mathematics, and there is no easy way. A friend told me that mathematics hurts, and it is supposed to hurt, and it hurts everyone. So if someone thinks that she or he has difficulties in mathematics which may discourage him or her, the only thing I can tell him or her: please don't. Nobody should be shy in this term. Okay, there are brilliant minds, but they are the exception, not the rule. To most people, mathematics is tough, and it is tough at any level. So the point I am trying to make is there is no easy way into and in the world of mathematics. So just keep doing, even if it is hard on you, even if it is harsh, even if it hurts. Just go ahead. You can learn whatever you want. Okay, in the meantime, I am just working with the optimized version of the Bellman equation by putting the optimum policy function back into the Bellman equation. We can find the optimized Bellman equation, and we can do the same simplifications as previously. Oh, hopefully I'm correct. I'm just double checking time and again. Okay, and this leads to the same, same in air quotes, very similar Riccati equation, the fixed point of which is matrix P of the value function. So we need to follow the same procedure to find the value function in MATLAB. So with iteration, we can solve this. This is a difference. Mathematically, this is a difference equation, a matrix difference equation, and the solution P, the matrix of the value function, is the fixed point of this Riccati difference equation. So if the initial guess is 0, we can start the iteration with this step. Okay, it's uninteresting. Okay, so if some final remarks regarding the solution, we want to understand the dynamics that this system implies, and we know that this linear equation describes the dynamics of the endogenous state. Sargent calls it the transition function, but in the language of the Stokey-Lucas book, the transition function refers to a function describing the transition of the exogenous state. So I don't want to use the expression transition function. So this is a linear function in my language. This is a linear function that describes the dynamics of the endogenous state. And if we have a policy function in this form, which can be made explicit by finding the solution by iterating on the Riccati equation. So these two conditions together lead to this equation, or simply put, this is what we have. This is a first order difference equation. If it is convergent, it converges to 0 because so this is the only option in terms of convergence. So if it is convergent, it converges to 0. So if this process is stable, then the stationary point must be zero, and we can decide if this difference equation is stable or not by checking the eigenvalues of the matrix A minus BF. If its eigenvalues are strictly less than 1 in absolute value, then this is a stable matrix, and this is a stable process converging to the stationary point 0. Next time we will go along this path. So we will try to map an actual problem with a quadratic transition function into the framework of the optimal linear regulator, and we will try to set up a MATLAB program to find the solution to the Riccati equation. So this is what we will do next time.